So, in the last occasion we discussed the electro-optic effect in isotropic medium, particularly we chose the gallium arsenide. We will take a break and we will go into some basics of the modulation properties, light modulation properties as far as this electro-optic crystals are concerned. So, we will be discussing these topics, understanding the electro-optic light modulation. We will start with the phase modulation for longitudinal and transverse configurations. Then we will be talking about the experimental setup and the principles of the amplitude modulation and polarization modulation. So, we divide this under two categories, that is longitudinal configuration and transverse configuration for this phase modulation, amplitude modulation and polarization modulation. These are the three very important properties of electromagnetic waves which can be modulated to develop various kinds of measurement instruments, sensors and several other technologies. Phase modulation. So, let us try to understand what phase modulation is, and we will first consider a simple case, very simple case of a plane wave, Z propagating plane electromagnetic wave, and let us assume that this electric field vector is oriented along the x direction. So, in that case we can write down this plane wave equation in the form of sinusoidal equation. It could be represented as an exponential phase equation as well. So, look at this, this x cap indicates the polarization, E naught is the amplitude and this is the phase factor. Now, these are the three things which can be modulated: polarization, the amplitude and the phase. Amplitude modulation is relatively simpler to understand. It can happen just by blocking the electromagnetic wave with a frequency, with the characteristic frequency of the modulating wave. There are, but in this case we will apply some electro-optic method to modulate the amplitude, but phase modulation and polarization modulation, they are slightly different to understand in this context. So, we will first talk about the phase modulation, then polarization modulation. So, in general we started with a simple plane electromagnetic wave which is propagating along the z direction and the polarization is along x. Look at the phase, amplitude and polarization, but in general for a plane wave passing through a medium of certain length, that is the travel length is finite, then in that case the input and output waves can be described in this form: E out equal to alpha B of x E input exponential I, this phase factor, which is also the property of the medium. So, alpha is the attenuation or it could be the transmittance by the medium, B is the polarization properties of the medium, phase contribution due to the medium is described by phi 1, this is the contribution of the phase due to the medium, and x indicates the properties which are related to the medium. So, there would be some sort of influence of the medium which will be appearing in this plane wave equation in the form of the polarization, the phase, the amplitude. So, for phase modulation, let us consider, look at this equation, let us consider that the medium is non-birefringent. That means, B is equal to unitary I. So, this B term does not appear here, and also consider that the medium's transmittance is alpha equal to 1, that is there is no attenuation, and then this previous equation, this can be represented as E out equal to E in and this exponential of phase factor phi 1. The phase retardation that depends on L and N. So, this is the very basic point to understand the phase modulation. So, this is the phase which is a function of the medium dependent refractive index that is seen by the propagating electromagnetic wave and the length of the travel. So, put together this is the phase. Now, if we can modulate this, length is L anyway is fixed, and lambda if we choose a certain monochromatic wave of wavelength lambda. So, this n, this L and lambda they are fixed, and it is only the refractive index that can be, that if we can modulate, which will in turn result in the modulation of the phase phi, and we will see how we can implement this phase modulation scheme in the case of electro-optic modulators. For polarization modulation, if we consider the linear birefringence, then there will be two specific states of polarization, the two eigenstates, and we can describe this polarization eigen matrix by this, where this phi 2 is the birefringence, the phase retardation, slow axis, fast axis refractive indices, and this is the length L over which the two polarization states are travelling. So, we can represent the effect of the medium through this matrix to relate the input and output electromagnetic wave. For circular birefringence, the medium induced changes in the polarization azimuth is given by this equation, where this phi 3 is the rotation angle which is caused by the medium. Phi 1 remains the phase, that is the medium dependent phase. Okay. So, for phase modulation, one can use a suitable cut of the electro-optic medium, electro-optic crystal. A light wave is phase modulated without changing the polarization or intensity, because otherwise it will be a mixed and will be difficult to decipher the phase modulation information. So, this phase modulation can be achieved, one of the two possible ways that is needed for a crystal and its orientation. One is that the crystal's principal axis does not rotate with the applied electric field, but the axis undergo change uniformly. So, this example we will discuss in the case of lithium niobate electro-optic effect, that when you apply an electric field along the optical z axis of the crystal, then the index ellipsoid does not rotate, but the length of all the three axes, three semi axes, they increase uniformly, and this results in the, because there is no, the principal axis, principal refractive indices only change its magnitude, but there is no change in the direction. So, you can have phase modulation if you apply a modulating voltage, then because this delta n of x or delta n of y alone will change with the modulating voltage, and as a result the output light will be phase modulated. We will see this example. Okay. So, the second way is that the crystal's characteristic plane perpendicular to the direction of propagation, where the plane rotates under the influence of the applied field. In the case when the plane rotates, then input wave must be polarized along one of the new principal axis, that is, after the electric field, after the rotation of the index ellipsoid, this x dash or y dash, the input polarization has to be along x dash or y dash, that is the new principal axis system. In that case, and the field will not alter this polarization during the modulation. That means that electric field, application of the electric field will be fixed, only there will be a modulating field. The result will be the modulation in the value of the x polarized refractive index or y polarized refractive index. The result will be reflected in the phase of the light that is propagating through the crystal. An example of this also we will discuss. We will see that a KDP, that is potassium dihydrogen phosphate, the electric field applied along its optical z axis will give rise to this effect, and we will see in details about this effect. With a polarizer, the second case, that if you have a polarizer sparse axis which is along the new principal axis x axis, and the light is now incident, but this axis will be active as long as the voltage will be applied in the longitudinal direction, in this direction. So, when the voltage is there, this axis will be active, and the value of this, the value of the refractive index will be starting from the base value, that is n 0 to the delta n value, which is proportional to the applied electric field. So, the phase will be modulated starting from the base value corresponding to the n 0 value to the new value, which is dependent on the applied electric field. So, as a result, but there is no change in the direction of anything, it is only this polarized light, and this polarized light will be out, only there will be a modulation in the phase, just because there will be a modulation in the refractive index, new refractive index starting from n 0 to the new value n x dash. The electrically induced change in the refractive index, this is the one which I mentioned just now, that is delta n x will be this much, but originally it was n 0 in absence of electric field, plus this will be the new refractive index. So, this is the effect which has come from the external field. For a longitudinal case, this delta phi phase, in this case, this will be just this multiplied by k 0 and the length of the crystal, that is E equal to V into L. If I write V into L and V by L into L, then this will give you that the phase which is, this is the phase which will be modulated over the base phase, that is related to the n x, not n x dash, independent, this phase is independent of length L and is linearly proportional to V. So, as you modulate V, then the phase will be also modulated. I hope this is very interesting. The electrically induced phase change will be this for the case of a transverse modulator with the applied voltage. If the modulator is a transverse one, then V by D is the electric field, which will be represented by this one, and as a result this will be proportional to L by D. So, corresponding half wave voltage for the case of longitudinal one, since delta phi this has to be equal to pi. So, if we put that delta phi equal to pi, this gives you a half voltage, half wave voltage, which is equal to this the new refractive index property, and for the transverse modulator the corresponding half wave voltage will be this. So, these are the voltages which are required to switch the modulator from state 1 to state 0 or vice versa, the way we choose the convention of switching the modulator. Now, in case of phase modulation, if the applied voltage and hence the electric field, if it is sinusoidal in time, the phase of the output can be represented by this. So, twice pi by x into n x dash plus additional this much of the phase. So, which can be represented as this. So, the light output is for phase modulated with the modulation index, which is equal to this value, because this is the total phase, new phase. From this equation, from this expression, it tells you that it can be developed into a Bessel series. Del phi E 0 of t can be written in the form of this equation, consisting of components of omega and higher harmonics. We will see this in the case of phase modulation for a particular crystal. Then it can have the component frequencies omega and n omega, where n equal to plus minus 1, those are the side band frequencies, and will be the modulation index delta. Now, we will discuss the amplitude modulation and how we can make use of this configuration of the polarizer, analyzer and the crystal in the case of longitudinal or transverse to get the intensity of the light modulated by the external electric field. The intensity of a light wave is modulated in several ways, using a dynamic retarder setup with a crossed polarizer, which is the most popular and most common technique to implement intensity modulation or amplitude modulation. Phase modulator configuration is also used, particularly using a Mach Zehnder setup, where you have two electromagnetic waves first split and then again mixed, and giving rise to depending on the phase difference between the individual arms, which will result in the phase modulation. Then by choosing a dynamic retarder with a push pull electrodes, these are the means to implement to realize phase amplitude modulation by external electric field. Intensity modulator with crossed polarizers, in this case we see that you have the pass axis of the input polarizer, which is along the old principal axis. It could be x or y. Then the light can be thought of split into two orthogonal polarizations, which are x prime and y prime. These are the new principal coordinate, principal refractive principal axis, and therefore, it will have equal share with x and y prime, which will travel along this length, but depending on the x prime and y prime refractive indices, there will be a phase difference, there will be a retardation, there will be a delay, and then because you have a crossed polarizer, so the output will be modulated. The output will be modulated depending on the applied voltage, because applied voltage will make this the two orthogonal polarizations amplitude dynamic because of the delay, and there is a quarter wave plate which is to come to bias this modulator. This is what we will call the optical biasing to shift the operating system to the 0 position, to the linear region, and this also we will see. And the transmittance can be represented by this I 0 by I, this is I output, intensity output by intensity input. Okay. So, let us consider light propagating in the z axis with z cut KDP crystal. We will discuss this just to give us some idea. With an electric field applied along z direction, then n x prime is equal to this, and n y prime is equal to this n 0 plus this quantity. N z does not change, it remains that extraordinary refractive index. Hence, the induced birefringence and the retardation are given by this equation, that is delta n x, which will be the retardation. So, n x prime difference n y prime will give you twice of this. So, that is what is appearing here, n 0 cube r 63 E z. Then E z, if you replace by the voltage, that is V by D, then the retardation, that is the phase delta phi will be, which is represented by tau here, for a specific purpose that we will use this matrix formulation to understand this polarization. So, this twice pi by lambda n 0 cube r 63 into V, this will be the phase retardation. So, the output polarization can be represented by this matrix equation, e to the power of I tau by 2, e to the power of minus I tau by 2, and then E 0 x dash, E 0 y dash. For a linear, to have a more clear understanding, for a linear linearly polarized light at the input, if it is represented by this 1 by under root 2 1 1, the output state emerging from the crystal will be this, which includes the effect of the medium with the retardation, that is tau it appears as tau by 2. So, the electric field affects the polarization state of the light transmitted at the output in this way. So, you started with this was the input, and now you get the output like this. For a linearly polarized light at the input of this state 1 0 or 0 1, oh this is by mistake, this should be 0 and 1, 1 0 or 0 1 will give respectively the output state from the crystal, which will be e to the power of I tau by 2 0, or corresponding to this state, this will be E out will be this. So, an electric field affects only the phase of the input light polarized along the principal axis. So, this is one of the principal axis, and the corresponding light is only affected in its phase. Here also for the other eigenstate it is affected in the phase. For a linearly polarized light at the input, that is you have both 1 1 and which is followed by a polarizer at minus 45 degree, the output state will be like this. So, this is now both of them and then 45 degree. So, you have the effect of 45 degree appearing here, which will result in this state. That is why you have sin tau by 2 appearing in the power output to power input. So, P 0 is the input, P out is the output power. For a relative transmitted power, if you look at this, if you take the square of this, so this will be equal to tau by 2 by I 2. So, this will give you that P out by P 0 equal to sin square tau by 2. An additional birefringence of pi by 2 is then needed because of this factor to bias the output for a linearized response. Now, intensity modulated with crossed polarizer, you have this T equal to I O by I input, I output by I input is equal to the transmission as the ratio of the input to the output intensity. So, this you have seen that this is equal to sin square tau by 2. You can rewrite this as 1 minus cosine tau, and you can further rewrite this as, because tau phase retardation will be equal to tau 0, the birefringence without the field, and this is due to the field, which is proportional to the field. V pi is the half wave voltage, and V is the applied voltage. So, this will appear in this form. We will see this expression later also for the specific kind of crystals at a given orientation, when we will be discussing about that. So, you have this expression that this transmittance is equal to half of 1 minus cosine tau 0 plus pi V by V pi. For linear modulation around 50% transmission point, a fixed bias of del phi 0 equal to pi by 2 has to be introduced here. This is done by placing an additional phase retarder. This I think we have shown earlier, an additional phase retarder by placing this quarter wave plate. It can be done by applying an additional voltage, but we will see that the disadvantage is it requires very high voltage. So, this can be achieved by putting an additional phase retarder in the form of a quarter wave plate, or by applying a fixed bias voltage which is equal to V pi by 2. In the case of natural birefringence, the values have to be changed accordingly. These values have to be changed depending on the natural, the magnitude of the natural birefringence. For sinusoidal modulation of the voltage, the retardation at the output including the bias is given by this pi by 2 plus del phi sin omega t. Then this del phi m is the amplitude modulation index, because this is the depth of modulation, the strength of modulation, amplitude modulation index, which is equal to this. This we will see that this del phi m is equal to pi V m by V pi is the modulating voltage V m, or it could be V 0 also. For sinusoidal modulation of V, when V m is much less than 1, that is for a very weak signal, very small modulating signal, the transmission becomes this, you can write equal to this, and you can see that it is proportional to the modulating voltage, because it appears in the form of this modulating voltage, linearly proportional to the modulating voltage. Now, we will quickly visit through the polarization modulation. This is again, this polarization modulation requires a dynamic retardation, and it involves the coherence addition of two orthogonal waves. The thing that is required to understand that in the case of polarization modulation, there is no change in the intensity or there is no change in the direction of polarization. The polarization axis will be same, but only the state of polarization will change at the output. And to do that, and you know that the state of polarization can be varied from linear polarization to elliptical polarization or circular polarization and back to linear polarization. This variation will be the modulated output. So, the result, it results in a change of the input polarization state at the output. So, the state of polarization will change, but the direction of polarization. So, the crystal and the applied field are configured in such a way that there will be a dynamic fast and slow axis excited in the crystal across the cross section. The polarizer is positioned such that the input light is decomposed into two orthogonal linear polarizations along these axes, along these two orthogonal eigen axes. And let us see this setup. You have an input polarizer which has this pass axis along the old principal axis of the system. Old, by saying old, I want to mean that in absence of any voltage, this is the principal axis system, principal axis x and principal axis y, and anyway principal axis z does not change, but once I apply the voltage, the principal axis, the new principal axis are x dash and y dash. So, I launch the light input polarization with which is halfway between the x prime and y prime, that is along the x polarization axis. Now, because x prime and y prime refractive indices along these directions, for these polarizations are different. So, they will develop a birefringence, but the polarization axis will remain same. So, as a result, depending on the applied voltage and hence depending on the retardation between these two polarization, that is x dash and y dash, the output polarization state will be changing from linear to elliptical and back to linear, depending on, in this case it will be circular if I give equal 45-degree inclination to x prime and y prime along when the polarization is along x axis. So, if light is travelling along the principal z axis and is polarized along x or y axis, the corresponding refractive indices of the first and slow axis will be represented by this x prime and y prime, and these are the values associated with these refractive indices, new refractive indices which are voltage dependent, electric field dependent refractive indices. these are Nx and Ny are anyway 0 N0. So, therefore, you have a birefringence which is electric field dependent birefringence, which can be represented by this. Now, Nx, Ny and Ry, Rx, these are the crystal's electro-optic properties, and this is a general way of looking at it. It depends on the specific crystal. So, delta phi is now, you can see that you have a natural birefringence of the medium, and this is the induced birefringence of the medium. So, delta phi 0 is the natural one, delta phi I is the induced birefringence due to the applied external electric field. In general, the output wave is elliptically polarized, but if your induced birefringence is such that, which is an electric field dependent property, voltage dependent property, is equal to pi by 2, then the electric field vector is circularly polarized at the output, but if it is pi, then it will be linearly polarized. So, by changing the voltage from 0 to pi, you can have linear to circular, linear to circular to linear and back to circular, and so on and so forth, by rotated by 90 degree to the input direction. So, this is how you can switch, you can change, you can continuously modulate the polarization of the output, and in this case the corresponding half voltage is given by this equation, which comes from this equation, that is the voltage which is required to switch the modulator, this must be put equal to pi. So, this is the phase that has to be equal to pi. So, that gives you V phi, the half voltage that is required for this modulators switching from state 1 to state 0 or so, and this is proportional to the wavelength lambda, as you can see. So, this half voltage depends on the wavelength also, is linearly proportional. Higher the voltage, higher will be the half voltage required, and it is inversely proportional to the relevant electro-optic coefficients, that is Ry and Rx. Now, so this cancelling this is one important requirement, that just to make this is the birefringence is just proportional to the applied voltage, we need to cancel this natural birefringence, which can be done by optical biasing or by applying a bias voltage. So, this retardation delta phi is made a multiple of twice pi, which can be done by slightly polishing the crystal to adjust its length, because it is length dependent, natural birefringence is length dependent, k 0 delta n x y into L. So, this L and all put together, if it is made equal to twice pi, then there is no natural birefringence, that is this term will not contribute, or by introducing a variable compensator unit just to compensate, cancel out the effect of this delta phi 0, that can be inserted. And a more practical approach is to tune the applying voltage by a small bias voltage, which will just cancel the effect of delta phi 0. So, by this discussion we have tried to understand how the phase modulation, amplitude modulation or the polarization modulation work in the case of light wave, and in the relevance of the electro-optic modulation by applying an electric field. So, we understood, tried to discuss this electro-optic light modulation in terms of phase modulation under longitudinal and transverse configurations. We also discussed the setup for the amplitude modulation and polarization modulation with the basic principles, and how the phase, amplitude and polarization can be modulated, tried to understand. Thank you.